Today I would like to discuss about photovoltaic cell. Actually, photovoltaic cell is a kind of photocurrent generator. So whenever there is no light fallen on the photovoltaic cell, so it behaves like an ordinary diode or a PN junction diode, which consists of a P-type and N-type layer as shown like this. So actually, before going to that, what is an intrinsic material? Intrinsic in the sense pure material, which is having a number of electrons is equal to number of holes, so that if we try to the Fermi level, it is somewhere here. Okay. So if it is an n-type material, we have to dope the intrinsic semiconductor with n-type material called pentavalent material, so that it will become excess in electrons, so that the Fermi level shifts to the top like this. If we take an intrinsic semiconductor and dope it with the trivalent element, which is having less than one electron in the outermost orbit. Actually, in intrinsic semiconductor, we have only 4 electrons in the outermost orbit. That's the semiconductor, pure semiconductor. Whereas for an n-type semiconductor, we have an extra electron, that is 5 electrons in the valence band, whereas in a p-type, there are only 3 electrons in the valence band. So if we try to draw Fermi level, it is somewhere here. So if we try to add these two things in order to make a PN junction, so that we'll get like this. And this is the barrier. The barrier is formed due to the immovable charge carriers formed due to temperature. So a barrier is formed in between P and n-type materials like this. So some free electron hole pairs will be created somewhere here in the valence band. So actually, in a material, let us suppose an n-type material, if we want to pump an electron from valence band to conduction band, we need to incur some energy. Okay, then where we get that energy? Actually, for an ordinary diode, we have to give that energy from some external source. Whereas in a PN junction, in a photodiode, in a photovoltaic cell, so that energy will be coming from the incoming photon radiation. So when this incoming photon radiation fallen on the photovoltaic cell, then that radiation will hit the free electrons present here and moves the electrons from valence band to conduction band. Conduction band, in the sense it is out of valence band. It is the electron become a free electron, free to move anywhere. If we connect a load across this, so show in the next. Let's see here. So in this slide, so this is the PN junction, and here we have a free electron and a hole. So whenever some light falls on these free electrons, what happens is so these electrons circulate through the node. Actually, the incoming light having some energy in the wave, according to Einstein equation, E is equal to h nu, is having some energy which is equivalent to the band gap energy to carry the electron from valence band to conduction band. Okay, so that this electron releases and passes through the load like this. So this creates a current called photocurrent. Actually, electron direction is opposite to the current direction. So here, so this is the photocurrent direction. As this is the electron direction, this is the photocurrent direction. So there is another kind of current in the PN junction, which is called energy due to decombination. So all the electrons released are kicked by the energy absorbed from the sunlight by these electrons will be pumped actually in this manner, but some of the electrons will recombine with the holes like this. So here also it will produce some current called recombination current. So totally we have two currents. One is photocurrent and the other one is recombination current. Actually photocurrent is only usable. So from the useful light, photocurrent is only useful. So part of the light will be wasted in the form of recombination current. So this is one of the causes to decrease the efficiency of the cell. Another thing and another important thing we need to discuss here is solar radiation having different waves of different wavelengths, having different energies. So we require the wavelength having energy which is equivalent to the band gap energy in order to from the electron from valence band to conduction band, and the other wavelengths will be the energy, there is a photon energy released by the other wavelengths will not be consumed by this electron. Okay, so will not be consumed by these kind of electrons, so that energy will be wasted in the form of heat. Okay, so that is the reason why the solar panel having only 25 to 30% efficiency practically. So incoming solar radiation, all the radiation will not be converted into electricity. Part of the radiation will be wasted in the form of heat, and only some of the radiation, which is the band gap energy, is equivalent. Sorry, when here the energy released by the photon having some energy which is equivalent to band gap energy, only that part of the that wavelength only will be useful to generate the photocurrent here. So this is equivalent to the diode like this. So the anode and cathode. So this is the p type and n type materials. The conduction from P to N and electron conduction is from N to P like this through the load. And these two plates are called charge collecting plates. Okay. So here is the original PV cell. So a cell consists of a P type material on the bottom, and here is the N type material. So as like in the previous case, here the P type material width is more as compared to the N type material. Why? Because when a light fallen on this N type material, this should be penetrate and reach the junction. Actually, these p electrons are present near to the junction, and this light need to somewhere here. So these p electrons are present near to the junction. So this light need to kick these electrons and pump these electrons to cross the junction like this. Okay. So this n-type layer should be as thin as possible in order to allow this light to hit or penetrate through the junction easily. So again here also we need two types of two plates, two charge carrying plates. So on the bottom of this p-type layer we are using a metallic structure, and that metallic structure itself acts as a positive plate, and here and all this is the n-type material, so we cannot connect any electrodes to the n-type material. So we are drawing some thin lines using some photolithography process. We have to draw some thin lines, thin conducting lines, so in such a way that it should not cause any obstruction to the light fallen on the n-type material, so that we have to connect some electric contact to these thin layers. So we can collect the current from the PV cell like this. This is the electron flow and this is the current flow as shown below case, before case. So this is the PV cell equivalent circuit, and this is the photocurrent and this is the diode, and RSH, RSH, and so here the RS represents the series resistance. The series resistance was the resistance offered in this part. Okay, so and RS, so this is RSH series resistance, and shunt conductance RSH is the conduction due to this recombination. That's a recombination conduction due to this recombination current. Actually, this is a kind of a leakage process. So this path represents a leakage path for this photocurrent, like this. So rest of the current will be fed to the load. So here is the load, and the output voltage V across this one is a function of the amount of voltage drop in this load, that is equal I into RL. Okay. So if the RL value is more, the voltage drop across this one is also more. So based on this, we are controlling the voltage across this one. Actually, this is a load dependent voltage. And coming to here, this is the ordinary diode. So whenever there is no load here, so this photocurrent entirely circulates through this diode only. Okay. So without that is when no current fallen on the PV panel or PV array, so some current I naught or dark current will be flown through this diode. So when some PV photocurrent, that is when current due to some incident light appears, so this part will come into picture. Okay. Anyway, this will be discussed in detail in the next slides. Then here we are already aware of this, and so based on the amount of current drawn by this one, the voltage at this point, so we can regulate the voltage by controlling the current drawn by this one by inserting some power electronic charge controllers here. So some power electronic device here, which are circuit here. So then this is the ordinary diode. This is the diode when there is no light fallen on this PV cell. So when light fallen on the PV cell, so this is initially PV cell. So when light fallen on reference, so this part will come into picture like this. So it will feed some current outside when we connect some external load. So when without connecting any external load, the voltage appeared across that is voltage appeared across this junction is known as VOC, open circuit voltage, and without connecting any load, if we short circuit these 2 points, and then it is known as short circuit current ISC. So this is about the PV cell when light fallen on this. So these are the characteristics of PV cell. So when no light fallen on the PV cell, so these are the diode characteristics. So when light falls, what happens? So these characteristics are pulled down like this. When the amount of light fallen increases, these characteristics will further down to this. So according to this equation, I is equal to I naught into exponential of, that is a diode current minus PV current will give us the load current I. Actually, PV current means that is a generating current. So we can rewrite this expression as I is equal to IPV minus I naught into exponential of QV by KT minus, and also we can neglect this minus one term in this expression, so that the characteristics will also get reversed something like this. So now the new expression become like this. Anyway, the photocurrent whose magnitude is very large, and ultimately it is based on the load, external load we are adding to the circuit. Okay, thank you.